We are from TUP Manila, and this study is entitled Influence on Concrete Properties of Tire Steel Wire as Fiber Reinforced and Crumb Rubber as Partial Replacement to Fine Aggregates.
The average waste production worldwide has been a general problem along with the increase of population, industrialization, and improvement of living standards. In the Philippines alone, there is an increase of 2,660 tons per day from 2012 to 2016. Rubber tire is one of the most problematic sources of waste as it takes 2,000 years to decompose and revert back to nature in natural process. Every year, over 1.6 billion new tires are produced and around 1 billion waste tires are generated, but the recycling industry only processed 100 million tires every year. In addition, used tires are often found discarded in natural environments, in rivers, and in ocean. This is one of the many reasons why a lot of industries have utilized tire waste in various applications such as crumb, rubber, concrete.
This study is significant to the following sectors. Second, locally, most of the old tires in the Philippines end up either in the landfill or get burned. This study can serve as a solution to avoid polluting the environment. Last, to the world, concrete as a structural material has played a vital role in the development of industries. With this apart, it is also known as one of the contributors to the climate change. This study promotes the incorporation of recycled waste material into the concrete to reduce the consumption of aggregate.
The process of pulverizing rubber tires is called ambient mechanical grinding, which is the shredding of rubber tires at above or normal room temperature. Steel wires will be separated using magnets and fibers will be removed by constant shaking and wind sifting.
According to EcoGreen, the resulting crumb rubber will have a size of 20 to 30 mesh or 600 microns.
After obtaining crumb rubber, it will be pre-treated with NaOH or sodium hydroxide that removes additives from the rubber surface, leaving voids and replace, giving the rubber a more rough and porous surface when compared to untreated rubber. The crumb rubber is prepared by washing it in tap water to remove all particulates before submerging it in a concentration of NaOH. After submerging, the crumb rubber particles are washed again by constant agitation of tap water through stirring until the pH level reaches 7, which takes at least 30 to 45 minutes, and then they are left to be air dried. Crumb rubber generated in the ambient mechanical grinding will then be subjected to different tests to determine whether it is an ideal replacement for sand as fine aggregates. The following tests are to be used. The design mix for the sample will follow the table presented. The control specimen will have 0 steel tire wires and 0 crumb rubber. Design mixes with 1 and 2% steel tire wires will be denoted as S1 and S2, respectively, while variation in the design mix with the integration of steel tire wires and crumb rubber will be denoted as ST0 to ST8, respectively. Concrete specimens will then be left to harden for a day before being cured in accordance to ASTM C192. Each specimen will be cured for 7 days, 14 days, and 28 days before subjecting to different mechanical properties tests.
Before the necessary tests needed, each concrete mix must first undergo on a test conforming to ASTM C138, known as a standard test method for density, yield, and air content of concrete, since the study also aims to attain a potential lightweight material. To fully determine its workability, the mechanical properties shall be obtained. The concrete specimen will be tested in accordance with ASTM C39, known as a standard test method for compressive strength of cylindrical concrete specimen. It will also be tested for split tensile strength following ASTM C496, or the standard test method for splitting tensile strength of cylindrical concrete specimens. Flexural strength must be obtained using ASTM C78, known as the standard test method for flexural strength of concrete using simple beam with third point loading. And lastly, its resistance to impact will also be essential in workability, thus it will be tested to drop weight test conforming to ACI 544.
For the results and analysis from the related studies, the graph below shows how particle fine aggregate and crumb rubber gradation. This shows that the crumb rubber passes the definition of a fine aggregate in terms of size. The crumb rubber is much closer to the minimum requirements than the natural sand. On the other hand, the dry weight of various types of compressed rubber granules ranges from 4 to 9 kN per cubic meter and usually increases with increasing rubber size and rubber wire content. From the study of Aggregates et al. In 2021, the graph shows different studies and the changes noticed in the density of concrete when crumb rubber was used to replace a portion of the aggregate. All of the studies suggest that there was a noticeable decrease in the density of the concrete with crumb rubber compared to the control, making it feasible component for making lightweight concrete. Here are the mechanical properties of the modified concrete specimen from the study of Yu et al. In 2016. The compressive strength of crumb rubber concrete were shown to be lower than the control concrete after the curing process of 28 days. Thus, replacing the fine aggregates with crumb rubber is better than incorporating the change in the mixture. Despite having a lower compressive strength than the control concrete, 30% replacement of fine aggregates still satisfies the requirement of C30 concrete. For the splitting tensile strength, actual compressive strength, and modulus of elasticity, increase in rubber clamps result in a decrease for each mechanical property. The same pattern has also been noticed as replacing a percentage of the fine aggregates results in a slight decrease, while replacing a percentage of mixture results in a noticeable change. For concrete link with the addition of steel tire wires, the following data was gathered. The table shows an increase in each mechanical property as the amount of fiber mixed to the concrete mixture increases. This can be attributed to the bridging action of the fiber in the concrete during cracking, which provides structural support.
For the fourth specific objective, results for dynamic strength tests reveal that the amount of crumb rubber used as fine aggregate has a relationship with the energy dissipated. As we could see on the graph, the amount of energy dissipated has increased as the amount of rubber increases. This can be attributed to the increase in total impact time. The final specific objective is all about the workability of the concrete. The addition of either the crumb rubber or the steel tire wire causes the workability of the concrete to be reduced. This is due to the rubber being hydrophobic and floating, that causes segregation. To end our presentation, we would like to give you an idea on how impactful the use of crumb rubber and steel tire wire in creating concrete could be. A kilometer of road that uses crumb rubber at its optimum percentage would consume 68,745 pieces of single passenger tire, while also consuming the steel tire wire of 44,143 pieces of single passenger tire.
The minimum thickness and width of municipal and city roads in the Philippines is 280 mm and 10 meters respectively. A single passenger tire contains approximately 5.44 kilograms of crumb rubber and 1.17 kilograms of steel wire. With these numbers, it is determined that paving a 1 kilometer road with the integration of the above-mentioned materials into the design mix will reuse approximately 16,417 passenger tires